Okay, so welcome to lecture 10 of our class. Today is an important lecture, but it's also a relatively, I think it's probably going to be a fairly easy lecture to understand because it's a transition lecture between what we've been talking about, namely exact inference to approximate inference. And you have a new reading assignment. I'm going to start following this book, the Wainwright and Jordan book, pretty closely, including we're going to use the notation from the book, which is going to be a little bit of a switch from the notation that we've been using, which hopefully won't trip up any of you. We will have a couple of slides talking about how the difference in notation is, but actually the notation is pretty close, so you won't find it too strange or alien. And actually, what would be very useful for you to do by Wednesday's lecture is to read the first 3 chapters of the book. Chapters 1 and 2 are kind of like a very, very brief overview of what we've already talked about. So it should be the case that you can breeze through chapters 1 and 2. Chapters 3 is really where the novelty for you guys will lie. And of course, this should say the 3 chapters here. Okay, so before we do that, today we're going to talk about sort of finish up on conditioning, this idea of recursive conditioning, talk a little bit about the inherent hardness, at least some results on the inherent hardness of the problem that we've been trying to solve, namely inference and graphical models. And then we'll finish up with loopy belief propagation and include a very, very classic result, which was one of the first results that came out that attempted to try to understand what LBP is doing and why. Okay, so let's just do a little bit of a recap, unless there are questions. We've been essentially doing exact inference all along so far, and today we're really going to talk about our first approximate inference method. In exact inference, we said that we can essentially take a graph and we can convert any graph into a triangulated graph, and a triangulated graph is really just a tree. And the form of the tree that it takes is it can be seen as a junction tree. And we defined messages on the junction tree. And we saw one particular type of messages where we essentially divide out the old and multiply in the new. And we do messages in both directions. And we follow the message passing protocol, very much like we saw in the one tree. And we saw that if it's the case that we send messages according to the message passing protocol, we have local consistency, which means that neighboring clusters along an edge in this tree share or agree with what they share marginally. And moreover, we saw that the message passing protocol renders this local consistency condition to be true. And we also saw that if it's a junction tree, that any configuration of the potentials that has local consistency, regardless of how we've actually got there, is one where global consistency is true. And so therefore, the message passing protocol run on a junction tree of clusters, namely one that has the running intersection property, is such that we've got global consistency. And again, global consistency means that if you're 2 clusters and you share a variable, then you agree on the marginal on those variables. So that means that that's a condition, certainly a sufficient condition for marginals. And in fact, we saw an even stronger condition that when we run the message passing protocol in those messages, it actually gives the marginals. So that's basically exact inference. We also saw that we could use other algebraic objects. And this is actually very useful in a number of contexts, a number of applications, that there's nothing really special about multiplication and addition, that we can define any commutative semi-ring and run exactly the same procedures. And in fact, you could define an abstract C++ class to do all this kind of stuff. And then the last thing we saw was that there's another point on the time-space trade-off curve that's achievable. And this is, I think, I don't need to go through this again. So this is essentially the pattern of the messages between 2 cliques. This is really, I think, the important transition slide for today's lecture, because we're going to be essentially crossing the boundary from this region here over to this region here, which is the approximate inference region. So what we said before was that this yellow region is where exact inference is possible. And as soon as we find a point in the yellow region, we can always go up and we can always go to the right, and we can always do both simultaneously. What we want to do is sort of understand the boundary, which is the left down boundary as much as possible. So we saw that we had this point from the junction tree. This is the junction tree that achieves complexity, time and space complexity, exponential in the tree width of the graph. We saw trivially we can achieve this point just by essentially, if we don't count the pre-computation stage, we can achieve linear time complexity and exponential space complexity by essentially memorizing every possible query. Again, that's not really realistic because we're not counting all of the pre-compute time, but at least it's once you sort of do the setup, if you're willing to spend enough time, you can do that. Something which also is not realistic but is maybe slightly less unrealistic is where we have order n space complexity and exponential time complexity, r to the n. So in other words, we can achieve that point if we're willing to wait a long time for each query, and it doesn't take any memory at all. But what we also saw was an interesting point here, based on recursive conditioning, where we could still retain the order n space complexity, but have a fairly substantial reduction in time complexity, this reduction here, from r to the n to r to the chi width times log n. So it's an extra log n factor up in the exponent. And how did we do that? Basically, the idea of recursive conditioning, the 3-cluster version was essentially where we sort of first iterate over, say, the variables in this clique here, and then we iterate over the variables in, say, the second clique here, and then we accumulate into accumulator alpha 2 given 1, and then we iterate over another clique here. And then we do the final accumulation at the end. And when we're done, we've got the value of the query we want. And what's clear is that the memory complexity is still order n because we're never storing anything. We're just sort of recursing down, and we're never using more than n order n storage units. But we're doing a little bit better thanks to the fact that there's a separation. There's sort of a separation extant in the graph. And that's the total cost becomes not exponential in the whole thing, but it's slightly less exponential. It's exponential in some sense in the path length, in terms of number of variables from the root to the deepest leaf. Yep.
So you said each inner loop costs C2 without C1,
yeah.
The C3 without C1. What happens with that? Why is C2 over C1 the biggest?
Well, I'm just, for simplicity, assuming that all clusters are the same size, but it's really just they don't need to be the biggest. It's really the complexity is going to be equal to is exponential in the total number of variables from the root of this tree thing on the right, like from the red to the purple. So in other words, if C3 has more variables than C2 and less an equal commonality with C1. In other words, the intersection of C3 and C1 and C2 and C1 is the same size, then C3, the path to C3, the purple one would be more expensive. Okay, but did that answer your question? Because I think you might have been asking a different question. So let me give you the opportunity to ask that again.
Should it be the case that the sentence in the bracket should be C2 and C3 are the same size?
Oh yes, that is correct. That is indeed a typo. So this should be C2 and C3. Thank you. Is that better? C3 and 3.2. Okay. Yep. Okay. Any other questions? There's always a chance of there being a typo. So if this is the reason why you ask questions, because maybe the reason why you have a question is because there's a typo on the slide. So, in which case, it's an extra good question. Right? Okay, so then we talked about recursive conditioning more generally, and as was mentioned in another question in the last class, this isn't always necessarily absolutely possible, but in the cases where it's possible to decompose the graph into these clusters which are relatively balanced in this form, the idea is that we can essentially do computation of this fashion. Now, one of the things that I added to this slide last time was the initialization, because I thought maybe that was confusing. Because of course, the initial alpha 1 has to be initialized to 0, and then these two accumulators have to be initialized to 0 in each one of these inner loops, the outermost loop. So basically what you're doing here in each one of these things is you're doing a new accumulation, and the new accumulation, maybe we should even look a little bit closer at this. We're doing a new accumulation for whatever is common with C2 and C1, right? Because we're only iterating over that which is in C2 but not in C1. So for this entire loop right here, for that thing, the commonality between C2 and C1 is a constant, right? And so we're only iterating over the novelty in C2. And then similarly, in this loop here, we're only iterating over the novelty in C3. And so that stuff that lives in this separator, these separators here, is in some sense constant for the purposes of that loop. That's why it's called conditioning, or cut. It's a cut set conditioning. We're cutting a graph into something that's very easy. And of course, these iterations here might be possibly done fairly easily if we can cut them into a graph with lower tree width. And the idea of recursive conditioning is to, once we've condition on C1, and then we condition on C4, namely we've instantiated the variables in C4 and C1, then we only have left in these lower leaf nodes of this tree to instantiate the variables that are in C9 but not in C4 and C1. Okay? So these need not be a junction tree, right? This doesn't need to be a junction tree. This is correct. For as long as the graph in some sense decomposes in this way, but there is no requirement for it to be or to satisfy the running intersection property. Okay. We just need to make sure that when we get down to these leaf nodes, all of the variables that are being summed over in this probability are instantiated. So like for example here, this thing here, the probability of x sub C1 to 5, the union, that is meant to correspond to C1 union C2 union C5. And so all of those variables have to be instantiated, and they are because we've instantiated all the variables in C1. Here we've instantiated the variables in C2 that are not in C1, and here we've instantiated the variables in C5 not in the union of C1 and C2. So therefore this guy alpha can be computed. And so this set of iterations essentially corresponds to the recursive conditioning idea on this graph right here. Okay. And the whole thing doesn't fit in on one slide unless I rotate. If I could rotate this screen 90 degrees, maybe it would. But basically the idea is that this yellow stuff over here, we're just sort of inserting this code here inside of this nesting. It gets inserted inside of that nesting level there. And so just from a simple analysis, we get that each cluster, let's say, has at most omega plus 1 variables, and so each cluster is going to have cost r to the omega plus 1. It's exponential in the size of the cluster. And then because the number of times, the greatest number of times that the innermost loop basic block of code executes is going to be equal to that exponential cost, up in the exponent times the depth of the tree, which in many cases can be made to be log n. And so that's this complexity there. So it requires the tree being of bounded depth. So that basically gives us this point here. Okay. Now, whoops, that's not right. Let's see if this works. Good. Okay. Now the question is, we have this frontier. By the frontier, I mean this blue squiggly line. You might get other points. You might be interested in other points on the frontier as well. Like, for example, maybe we're interested in these points here. Now, is there any reason to get any of these points that I just outlined? Probably not, because once you've got a point for basic recursive conditioning, why would you want another point that has the same space complexity but worse time complexity? That doesn't make any sense. There is a way. There's a whole class of algorithms that can sort of almost smoothly go between the basic recursive conditioning point and the junction tree point. And we don't have time to talk about them in detail, but here's roughly how they work. And let's just look at this tree for a minute. So let's say that we've got C1, C2, and C3. And let's say that just for, hopefully this will work. Let's say that this is A, B, C. And this is B, C, E, and F. And this is B, C, G, and H. Right, so the point is that and so that basically means that this separator has BC in it, and this separator also has BC in it. So now we have that top level loop where we are instantiating all these three variables, A, B, C, right? And so that means that this BC is actually sitting there instantiated. So then for that BC, we then iterate over the residual, which is EF. We do all this stuff, and which is going to be R squared, right? Because let's say everybody has R possible values. So now let's say that the outermost loop is A, and then BC are the inner two loops within this thing. But then at some point we get a new value of A, and we have the same value of BC, which was instantiated it from some earlier value of A. Right? So if this isn't clear, it's kind of like thinking, let's say that this outer loop here is, and you say for x of A, for x of B, for x of C, right? And then so you have this stuff here. So inside of this block here, down here, BC is instantiated, right? And so therefore, when you go back and you change the value of A, you're going to get back to a point where BC is going to be instantiated to exactly the same value. And so therefore, that accumulation over EF is going to be wasteful and redundant. So that's exactly the thing that the junction tree does to avoid that redundancy, but at the cost of some memory, because you're now storing values in the separator tables corresponding to that which is common between the two cliques. Like what we could do instead is we could do some sort of caching or memoization, where once we've bothered to do this accumulation down here over EF for a given value of BC, why don't we just cache it? We could sort of, in some sense, even have a hash table where we hash on BC. So we have this loop down here. Once we get to this point, we do for B and for C, and we check the hash table. Does that value of B and C exist in the hash table? And if it's so, then we just say, oh, great, we get back the accumulation over EF that's stuck in the hash table. If it's not in the hash table, we just go ahead and do the accumulation. And when we're done, we stick it back in the hash table for that new value of BC. So how big is that hash table going to be? Well, let's say that if this was a K tree of some sort, then the separators would be of size omega, which is the tree width. And so the hash table would be, in the worst case, size r to the omega. So that suddenly means that now we've gone back to using space complexity, n times r to the omega, but at the same time we've recovered time complexity, and we've gone from this point in the recursive conditioning case to this point in the junction tree case. And that can be done recursively as well on the left side, but also, of course, recursively in the whole tree. So basically, we can do the recursive conditioning idea, but when we get to these separators, we essentially treat them, we memoize them, or we treat them as sort of hash table entries, so that when we encounter common separator values that have been previously instantiated, we don't need to redundantly compute them. Now, the question is, well, how do we get points in between? Well, what if we just don't bother caching all of it? What if we have a fixed size cache? What if rather than a cache of size r to the omega, we have r to the omega half? And we do replacement. Like there are lots of replacement strategies, like least recently used, and all sorts of other elaborate schemes for deciding if your hash table runs out of space, what you should not, what should you replace with something new. But you can see that for each size, required size hash table, you are getting a point along this arc. As you do more and more caching, the space complexity is going up, but the time complexity is going down. And so you can get any of these points just by how big of a hash table you want to use, using the idea of recursive conditioning, until essentially the hash table is of size r to the tree width, which case you've sort of recovered the junction tree algorithm, but done in a very, very different way. It's not done as a message passing procedure. It's done as a search, very similar to this thing. Okay. So does everybody see that? It's pretty cool, actually. It's pretty neat that one can do that. Now, it turns out that there's even more intricacy that one can do. So we haven't talked a lot about what happens when you have sort of value-specific independence. You can actually have probability distributions where A is independent of B, given that C is equal to the value 7, but A is not independent of B if C is equal to the value 2. It's like context-specific or value-specific independence. You can also have it be the case that certain summations are cached, and certain summations aren't cached. And the basic principle here is that when you condition on a set of values, all of the values that are not yet conditioned on, not yet instantiated, the probability distributions of those values might have very, very different factorization properties. And so therefore, once you've conditioned on something, you might actually then do a very, very different strategy underneath. Like, for example, you might condition on one set of values and then run some sort of belief propagation on a junction tree. You might condition on another set of values and do further recursive conditioning. Or you might sort of interlay recursive conditioning and junction tree and recursive conditioning, depending on the current conditions of the remaining uninstantiated variables that you haven't yet iterated over to get your value. So as you can imagine, this gets very, very complicated, and it does. One way of doing this is to sort of memoize dependency sets. So like a dependency set is essentially a set of variables and their instantiations. And then the idea is that once these variables have a particular value, you can memorize what happens, what's the subsequent consequence. Right? Like, so the subsequent consequence could be, on the one hand, the thing that we saw before, where we sum out the remaining values that are remain to be summed out, and then you cache them. It might also be the case that you sum out those values and you find that you end up getting a big, giant computation at 0. And those are called no-goods or conflicts. And so what the cache value might be is a 0. So then basically you don't even need to check. Like, once you get that value, you just say, oh, that's a 0. And in general, there are lots of search heuristics for trying to do that. When you have very sparse models with lots of context-specific independence, these zeros can save you an enormous amount of time, because what you don't want to do is you don't want to iterate over all your variables and then discover these zeros at the very, very last thing, because that basically means you've expanded this whole tree and you have all of these leaf nodes which are 0. What's a much better strategy, and which is something called the fail first heuristic, which actually was first articulated here at the University of Washington, by the way. The fail first heuristic is something where you say you want to find the zeros early on in the tree, so that when you find a 0, what you're essentially pruning away from the search space is this massive exponentially sized piece of tree. So the idea of the ordering of what variables you choose to iterate over first and which dependency sets you wish to learn first is really important, and in practice can make sort of differences in, massive differences in speed. I've personally seen differences on the order of like a factor of 10,000. I mean, these are major, major changes in speed, depending on just the order of the variables that you iterate over and how you deal with these zeros that you find and these cached values that you find. So that basically is all of this stuff down here. So in some sense, this doesn't really need to use cliques. We can do this in terms of cliques or clusters of variables or even individual variables. And in general, the idea is that these dependency sets, some of them might correspond to a clique or cluster. Some of them might correspond to something else. And the reason is that once you've instantiated a set of variables, because the dependencies, because the factorization of the remaining variables might change, each set of instantiated variables might essentially effectively give you a different junction tree. Because if you're to think of these as junction trees, because the factorization properties change depending on what you've conditioned on. So you can still kind of think of these as junction trees, but most people, I mean, when you look in the literature on algorithms like value elimination or recursive conditioning, this is, I think, this is a great paper, by the way, the valuation elimination paper. It's already 11 years old, but it's still, I think, very modern in its outlook on this type of strategy. It's a very general property that talks about no good caching and what he calls good caching, namely summations that don't sum to 0. But they usually don't think of these things as junction trees anymore, because the fact is that the junction trees in some sense change every time you condition on something, when you have lots and lots of value-specific independence. Now I should also mention that these approaches have made it such that problems primarily in the SAT and the CSP community that people thought earlier were impossible to solve because they were NP-complete problems. This is something that you see oftentimes, that you see in papers, this constraint satisfaction problem is NP-complete, therefore we resort to approximation methods. But that doesn't mean that any particular instance of a constraint satisfaction problem is such that you can't find a way of computing the exact solution. And what the CSP and the SAT communities and the people who've sort of been inspired by them, including people in the graphical models community such as Bacchus from 2003, people like Rena Decter, and also people like our own Pedro Domingos, they've been inspired by the CSP and the SAT community to say, well, look, we can actually push the forefront of what can be done exactly. And many of these problems that people originally thought were intractable just because they were NP-complete turn out to be computable. Instances turn out to be computable. That doesn't mean that it scales with n, but it does mean that the frontier of what you can do in practice exactly is greatly expanded above and beyond what people earlier thought, especially those who sort of gave up immediately after knowing that the problem was NP-complete. So, and like I said, these things then spill over into just general graphical model inference, even though they've been developed mostly, but not always, in these communities. Okay, are there any questions on that? I mean, like I said, we could easily spend several weeks on this idea, but I think a good starting point is this paper from 2003, if you're interested in this. Okay, let's move forward then and talk a little bit about hardness. So even if we do conditioning and search and all this kind of stuff, you know, at one point or another, the complexity of inference is going to be exponential, at least in the tree width. So as n is growing, as the number of variables are growing, the asymptotic complexity is going to be exponential. And it's exponential in the tree width of any covering. And so what we talked about before just a second ago was, of course, that these coverings can change. You might instantiate one set of variables, and your covering, your k-tree covering might be different depending on the certain values of the variables you're conditioning on. Okay, but you know, fundamentally, there is still this idea that the complexity is based on this k-tree covering. Okay, and so basically, we want to find the smallest k-tree covering, but as we saw, you know, finding the best exponent, finding the smallest omega, is identical to finding the minimal tree width, or finding the tree width, or finding the smallest covering triangulated graph. And we saw that that's an NP-complete optimization problem. So it's impossible, if we've got an arbitrary graph, to actually find the best way in all cases. Unless we do, at least until we know that p is equal to np, which most people believe it's not, it's impossible to do that in general in polynomial time. But then, to make it even worse, the problem even worse, or more depressing, that doing inference itself, even if you found the exact way of doing inference in graphical models, if you have n variables, is going to itself is an NP-complete problem. So you might solve one NP-complete problem to find the optimal way of doing inference, but doing that is an NP-complete problem. So it's like a nested NP-complete problem. And what we want to do is try to understand why that is. Like, why is inference in general hard? And we're going to see that it, in some sense, trivially reduces from the SAT problem. So what is the SAT problem? SAT is one of the first NP-complete problems that was articulated back in Cook's famous 21 Problems paper from 1970. Did I say Cook? I meant Karp, of course. Cook didn't list the 21, Karp did. But basically, the idea of 3-SAT is the following. So you've got n variables here, and you have a collection of m clauses, which you can think of as constraints. And each clause consists of a disjunction of at most three literals. So disjunction is like an or of 3 literals, and a literal is basically either a variable or its negation. So these are all binary variables, by the way. So it makes sense to talk about a variable or its negation, and that's a literal. And then clauses themselves, each clause, which consists of these 3 literals, this disjunction of 3 literals is organized in a conjunction, which is an and function. And the question, the yes or no answer of which is the NP-complete problem, is the following. It's basically asking if there is a satisfying assignment. In other words, is it possible to assign the set of binary variables such that this logic expression evaluates to true? And so here are some examples. You can see that the variables are x of I, and the negation of the variables is x of I bar. And so this is one clause, and this is another clause. And each clause consists of a disjunction of literals, which consists of variables or their negation. And then we've got this conjunction over the clauses. So I think that that's pretty clear, right? So that is known to be generally hard. So in order to show that inference in Bayesian networks itself is NP-complete, this is actually true for Markov random fields or Bayesian networks. We're going to show in some sense both. All we need to do is find the Bayesian network that represents this problem. And we're going to do this by using the max semi-ring. Because the max semi-ring basically says, find me the maximal, the assignment of random variables that has max probability. So let's define our set of variables. So we have n variables, which are binary. And let's say that Ci, which are in some sense our cliques, each Cj is the index set of variables that live in clause j. Okay, so those are if we have one clause that involves literals x1, x3, x5, and that's the jth one, then Cj will be 1, 3, 5. And we have m clauses. And what we do is we define a function, f sub j of x sub Cj, that evaluates to 1 if and only if that sort of particular clause is satisfied by the current assignments of the random variables x of Cj. Okay? And if it's not, basically f is a binary valued function. It's just basically the value of the expression, the value of the clause itself. It's pretty clear. And so what we end up getting is this formula. We just multiply these things together. So that thing, if it's the case that stat is satisfiable, then equation 10.3 can evaluate to 1. I mean, it's possible for there to be a set of values of x such that that product is equal to 1. Okay. So right away, that basically gives us a Markov random field for which, if we could compute the map solution, namely the values of the random variables that maximize the probability. So just to make this clear, we would have the probability of x would be proportional to this thing. And anything that maximizes the probability would have to have that f, that this product here, all evaluate to 1. Okay. And if that's true, then those random variables back in the original SAT problem would be a satisfying assignment. How do we do this in a Bayesian network? Well, we add a couple of additional variables. Let's add these variables y. And let's add a bunch of conditional probability tables of the form, this form. So it's saying that the probability of y sub j, so j corresponds to the jth clause, and we have one variable y for each clause. And saying that the probability of y sub j is equal to 1, given the variables in that clause, x sub cj, that evaluates to 1 if it's the case that the corresponding function on those variables is equal to 1, and otherwise it evaluates to 0. And then for all these other variables, doesn't matter, we just give them uniform values of 0.5. And so this gives us this joint probability distribution. It's a locally normalized Bayesian network joint probability distribution. And then we can, let's see, we would essentially instantiate all of these y's to 1, and then do the map inference problem on this Bayesian network. So here's an example. We have 5 variables and 6 clauses. Here they are. So x1, x4, x5 corresponds to y1, x1, x1, x4, and x5, and so on and so forth, you can see. And the idea is that the red variables correspond to y's. Those are all equal to 1. They're instantiated. And the x variables are hidden. Those are uninstantiated. And you're trying to find the most probable assignment to the x's, which, if you find the most probable assignment and it evaluates to 1, then you found a SAT assignment to the original SAT problem. So therefore, inference in Markov random fields, inference in Bayesian networks is NP-hard.
What are the bars, sir?
In this particular case, the bars correspond to the negation of a variable. So a literal is either a variable or its negation. And I realize that we're a little bit overloading notation a little bit. But so like here, these are binary variables, x1 or x4 or not x5. And probably, if I had been consistent with the notation we've been using before, this would be x1 or x4 or not x5 or something like that. But what we've been using bar for is in fact, I even wrote a little bar over the y to say that they are observed. But in this is the notation that's typically used, probably because it doesn't take as much horizontal space as using this little not symbol there. So. But hopefully that's clear. And even though we're overloading the bar notation a little bit, it causes no confusion. Yep.
Slightly lost. So the thing is, you have these variables and variables, and let's say n peaks. So for each peak, you have this indicator variable with which you connect it to these sum of the subsets of these variables, which are part of the peak. And now you are trying to tell that if you find the maximizing assignment, then the product of values of all these variables that represent the clique indicators will be 1.
That's right.
And that kind of just reduces down to satisfiability.
That's right.
You have 3 variables.
That's right. Because if the maximum assignment, because remember, what you're solving by the maximum summary is the most probable assignment. If the maximum probable assignment of those random variables is 1, then it must be the case that every single one of the products is 1 as well, which means that each one of the clauses are 1, which means that you found a set of variables that satisfy the SAT problem, satisfying assignment.
But what if you have only 2 cliques in the graph? So then I would have only 2 SAT kind of instances that kind of come out of this. So
do you mean, what do you mean by 2 cliques? So do you mean you have 2 clusters, or do you mean that each clause has only 2 variables?
Yeah, each clause has only 2.
Yeah, that's not an NP-complete problem. So 2 SAT is not NP-complete,
Right.
but 3 SAT is. As soon as 3 SAT is already NP-complete. So it's known that you can do 2 SAT in polynomial time.
Right. So if I can reduce my graph into containing only these pairwise kind of factors and introduce 1 variable for each of these pairs, then wouldn't that be equivalent to solving?
No, 2 SAT is not equivalent to 3 SAT. The fact that 2 SAT can be done in polynomial time and 3 SAT can't be done in polynomial time must mean that they're not reducible.
Yeah.
So, at least not without an exponential expansion.
From these 3 clique kind of things to 2 cliques, right? And where is that?
Not without an increase in complexity, right? You could do that, but that might lead you to an exponential increase. So. You can't just do that. We're going to talk about that order reduction, but the thing is that the order reduction leads you to variables that become exponentially big in the cardinalities of the original ones. So we'll see that. So you can sort of mathematically just treat things as pairwise. But anyway, this you can mathematically treat things as pairwise. That doesn't mean that the number of random variables is still 2, for example.
No, the number of classes will just explode. That's what will happen. Right?
Yes. And you're interested in if it's exponential in the number of random variables, the original number of random variables. Okay, so right, so 2-sat is polynomial solvable. So I think we're here. So basically this means that doing inference exactly is NP complete. So this doesn't mean that inference is always intractable. Where intractable in this context means we're talking about it in sort of the practical term. It doesn't mean that exact inference is always impractical. And like I said a little bit earlier, the work that's been done on things like value elimination and cache-based and recursive conditioning has shown that you can push the frontier, push the limits of what can be done practically for exact inference. But at some point or another, this NP-complete problem and exponential complexity is going to catch up with you. One problem can happen even if it's the case that random variables have a large number of assignments. So if random variables have a cardinality which is exponential in some original graph, say you do a reduction, then that's going to be difficult. You're still having to iterate over these things, over these variables. Okay, so this is now a transition to approximation. So let's just recap. I think this stuff maybe we don't need to do. We talked about the junction tree here. I'll just do it very briefly. How's that? There's the junction tree. We talked about conditioning and recursive conditioning, which gives you a different trade-off point. We talked about that it's possible to actually achieve many different trade-off points on this frontier. But at some point or another, you're going to have to do approximate inference. So the idea is that one way of looking at this is sort of in this picture here, and you say, okay, I'm going to be at this point. I can only afford this amount of time complexity and the corresponding amount of space complexity. But this isn't really done. What I'm about to describe you, it's not really done that often. But the idea is that you could have a third axis, which is kind of like the distortion. And so you could say, okay, I am willing to have this amount of distortion, and that's going to have its own trade-off curve, time-space trade-off curve. So for every amount of distortion, you have time-space trade-off curve. And in general, as the amount of distortion increases, the time-space trade-off curve gets better. And in fact, if the distortion is large enough, you can do inference in constant time and constant memory, right? If you're willing to accept complete noise, so much distortion that's complete noise, I could give you the answer. The answer is 4. That's your query, and that's within the bounds of the distortion. So obviously that's not useful. So, but you can imagine sort of this ever decreasing set of curves that basically at 0 distortion ends up being this curve here. But the analysis along this other axis is not typically done. But one should be aware that, at least conceptually, that exists. That whenever you're talking about approximate inference, you have to either be in the time-space trade-off curve for a particular distortion, or if you're not worrying about distortion, you're back to this 2D plane, and you're somewhere down in this region down here, right? The unachievable region. And again, the idea of unachievable means it's unachievable. It's not possible to do exact inference. Okay, so this next slide will be kind of the outline of the rest of the class. Okay, so let's do this next slide, and just as in terms of a big picture, let's make sure that we've got it before we get into the details. So when you do approximate inference, there are generally 2 approaches. You can get an exact solution to an approximate problem. So the idea is that you've got some problem, and you come up with some new problem, which is an approximate, and then you do all of the methods that we've been doing before. Like one possibility would be to do a structure learning procedure, like finding the best one tree, finding the best 1 tree turns out to be actually something that can be done fairly easy. But finding the best k tree is not easy. But still, you could find some k tree. And let's say k is small enough so that you could do exact inference on that k tree. I mean, it's still exponential in k, but if k is 3, and r is not too big, you could still do exact inference and construct a junction tree. And then you find the exact solution to that k tree, which is an approximation to the original problem. So another strategy is to do sort of functional restrictions of the model. It's another way of doing tractable inference. Like the idea is that the factors or the potentials might obey certain properties. And one very promising approach, which I talk about in one of my other classes, is submodular restrictions. So like you could, for example, ask for your potentials to be submodular, or you could actually decompose them into submodular and supramodular pieces, and then do algorithms that are inspired based on that, none of these pieces have any tree width restrictions. They instead have manner of interaction restrictions that, because of the manner of interaction, even though that they're not k-tree restricted, render the problem polynomial time solvable sometimes. Or the approximation. Remember, it's approximate model. The approximate model can be done in polynomial time. So another approach is to do sort of an approximate solution to an exact problem, which is maybe called approximate inference. So this is the dominant theme that historically has happened in the machine learning community up to maybe more recent days, when I think there's a lot of interest in doing this stuff right now, I think. But what we're going to be talking about in this class is approximate inference, like other forms of propagation, variational approaches. We'll be talking a lot about that, and various forms of linear programming relaxations followed by rounding. We'll be talking about that and how these things are similar to each other. It's also sampling-based approaches. Oh, I should also add, to this things like loopy belief propagation, which we're going to be talking about today. Sampling approaches and pruning is another good one. Pruning approaches are used quite frequently in sequential graphical models, like hidden Markov models. They came from search, and there's a lot of others. But the idea is that both methods are guaranteed only to give you approximate quality solutions. And it's actually, in general, really hard to characterize the distortion, because like what I said, this sort of time-space distortion, three-dimensional trade-off, is not really that well understood still. There has not been that much theoretical work on that. Although conceptually, I think it's clear that that exists. Okay. So let's take a break, and we will come back and talk about belief propagation. Okay, let's start talking about belief propagation. And belief propagation is sometimes called loopy belief propagation, and sometimes people say belief propagation when they really mean loopy belief propagation. But of course, loopy belief propagation when you have a tree isn't loopy belief propagation, it's just belief propagation because there are no loops. So therefore, they just call it belief propagation, and they think the word loopy is redundant. So whether you hear it called loopy belief propagation, LBP, or just belief propagation, oftentimes those are synonymous. So the idea, again, is to perform these generic messages, mu I to j, which sends a message from I to j. And we actually defined this message a number of lectures ago in the following way, where we basically, I guess, we have this edge I and j, and we have all these other guys here coming in, and the idea is that the message comes in from each one of these into I, and once we've received all of the messages into I other than from j, we can send that message out there. And that's what it corresponds to. And if it's the case that the graph is a tree, and we obey the message passing protocol order, then we reach a configuration where we actually have the marginals. The unary marginals are of this form, where essentially we just multiply in all messages that come into that node, and where the pairwise marginals are basically where we multiply in the two sets of messages corresponding into the nodes I and j, other than to each other, and then multiply in the original potential function there. And of course, we normalize if we want to get it locally normalized. These are all proportionality things. oftentimes it's the case that we actually have factors associated with not just the pairs of, of nodes along an edge, but we also have sort of unary potentials. I'm doing this here. I'm adding this notation here because we're going to start seeing this a little bit more. But the idea is that it really doesn't change anything, because let's just zoom in on equation 10.8 for a second. Like I could easily just, or I should say, we could easily just sort of treat this as one pairwise potential over ij. And in other words, this guy would just get absorbed into that one. But sometimes you see it where the unary, where this is the unary potential. It's unary because there's one variable involved in that function. Sometimes you see it being separate, as done in equation 10.8, and also done in equation 10.9. And 10.10, but 10.10 you don't see them. Okay, so there should be no confusion there about that there might be unaries and pairwise potentials. By the way, the other thing that I should know is that the unaries often have information about the evidence. Like if you have a Markov random field or a hidden Markov model, that's where the evidence comes in. Is that clear to everybody? Raise your hand if that idea is clear. Okay, this is an important point because I haven't really said much about evidence. So let's say that you have a hidden Markov model. So the idea is that in this particular case, so we're using x as the variables we're interested in. So in the case of hidden Markov model, let's just call this guy. This would be x1, x2, x3, x4, and x5. And this is y1, y2, y3, y4, and y5. And if it's a hidden Markov model, we're saying that the probability over x 1 through 5 and y 1 through 5 is proportional to, and we've got a bunch of factors over the pairwise guys. So we've got the product for say t is equal to 1 to 5 of say phi of t and t plus 1, x of t and x of t plus 1. I got a space there, but basically this stuff here corresponds to those edges here. And then we also have times phi of t of x of t and y of t. Right, and this whole thing lives in inside of the product. So that means that all of this stuff down here corresponds to these guys down here. Okay, is that clear? So that's a hidden Markov model. Now the idea is that in a hidden Markov model, typically it's the case that you treat these as observed. So we're using the bar over these. These are all observed. They don't actually affect anything. The only thing that you can iterate over are the x's. The x's are the hidden variables, the y's are observed. They're essentially constants that aren't involved any longer in the process of inference for the hidden Markov model. And so this function here, phi sub t of x of t and y bar of t, you can just sort of treat to be equivalent to some phi of t of x of t. It's just a unary. You know, that there is evidence there is just implicit, but it's really only a function of x of t. And so therefore, getting back to this thing, it could be very well the case that there is really, inside of this function here, there is some y of I as well, bar. But we're just not naming it. Since it's out of the picture, it's not going to change how we do inference. It doesn't change the factorization property. Okay. And then a Markov random field is exactly the same thing. In the case of, say, image processing, like there you just have a 2D grid. So I'm not very good at drawing 2D grids, but basically the idea is that you have this Markov random field, and all these guys are the x's. So like this would be like x of ij, where you have two-dimensional axes, and then you have hanging off each variable an observed variable. Right? Just like a hidden Markov model, except it's a two-dimensional. So in some sense, this type of Markov random field that you typically use for image segmentation is really the natural two-dimensional generalization of hidden Markov model. And these potential functions, the ones that I'm going to highlight in purple, these are the unaries. They're a function of two variables, but one of those variables is always instantiated. If this is image processing, if this is computer vision and you're doing image segmentation, then the observed variable would be the pixel value, and the corresponding hidden variable will be the label. Is it foreground or background? Or what type of object is it? Is it a tree or a car or a bus? And then these guys up here, the grid structure is the actual Markov random field. That's the thing that we do the inference on. And so therefore the unaries, those purple things, we can just sort of treat and think of as being variables, being functions only of that one hidden variable. And so we don't need to actually mention the evidence when we're doing inference because it doesn't change the inherent factorization. Interestingly enough, there's a lot of excitement, to put it mildly, about deep models these days. And it doesn't change. Each one of these could be a little deep model. They could be a deep model that maps from some windows of pixels into a variable. And then you have a Markov random field which smooths over the outputs of these deep models over the image. Or it could be a Gaussian, or it could be a histogram, or it could be anything that you want that associates a region of two-dimensional object, like an image, associates that with the hidden variable at that corresponding point. Okay. Oh, question?
Okay, I have a very, very basic question.
That's a good question.
The term inference itself means that we are inferring something based upon some evidence, right? So our distributions will change based upon whatever evidence we get.
The distributions change, but not the factorization. So you can think of it as we're still within the same family, where our families are, in this case, are associated with how the function decomposes, how it factorizes. So yes, the numbers that we're going to get from each of the instantiations of the x's will differ depending on what the evidence is. Like this pixel in the middle of the image, in one case will be a truck, in the next case there'll be a pineapple, in the next case there'll be a building, right? And so, but that's fine. I mean, the factorization is the same. And this whole thing, this whole class, we've been talking about doing inference in a way that amortizes the cost of doing inference over all of the members of the family of that that graphical model. Now, one thing that we haven't really done here is talked about higher order potential. So, like when we do this kind of thing here, when you do these messages, let's go back to this guy here. This is basically a pairwise message, right? It basically requires, that along an edge in a graphical model, there's a pairwise potential, psi ij of x of I of x of j. It really doesn't, that message, and we sort of arrived at those messages from looking at trees in the case where we really do have pairwise potentials. Okay, but the question is, what do we do when we have higher order interaction, like psi sub c of x of c, where the size of c is greater than 2, which could certainly happen. So remember a factor graph? So a factor graph, we briefly mentioned it at the beginning. What a factor graph does is it sort of explicitly gives you different nodes. It's a bipartite graph, where on the left-hand side you've got variables corresponding to our original random variables. On the right-hand side you've got nodes in the bipartite graph, which are these blue things, these blue squares with gradients in them, that correspond to the factors. So in this particular case, we've got the probability of x1, x2, x3, and we have variables for x1, x2, x3, and that involves factors f1, x2, x3, f1, f2, f3, f4, which has these factors here. And we can see that f2, for example, involves variables v2 and v3. So that gives us this thing. Okay, so it's a factor graph. It tells us the factorization, but it represents it explicitly. And it's easy to see that we could easily extend this factor. Like suppose we wanted to have, we added one more edge here, then that would change f3 to be, it would also be a function of x2. This factor would also involve x2 as well. Yep.
Will we be able to accomplish the same thing by adding hyperedges to a macro?
Yeah, we're about to do that. Yes, exactly right. And you've anticipated 2 slides into the future. So we're gonna, in fact, we're going to talk about a couple of different strategies. But then we're going to define the one that we're going to do. So, in fact, what one can do then is, in order to deal with higher order functions, we can define a belief propagation directly on this bipartite graph. In the case when the hyperedges are basically the things on the right of the bipartite graph, the factors. Hyperedges are basically bundles of nodes. It's a regular graph when the hyperedges are of size 2, and it's a hypergraph when the regular edges are of size not necessarily 2. And with this graph, we could actually define belief propagation. The thing also, interestingly enough, about a Markov random field is that it doesn't really distinguish between higher order potentials and lower order potentials. And what we mean by that is the following. This is a little bit important because this is about generality and specificity of a Markov random field versus a factor graph. So let's talk about these 3 graphs here, G1 and G2 and G3. So G1 and G2 correspond to factor graphs. These are hypergraphs or bipartite graphs. And then G3 is just a regular old Markov random field. The idea is that the variable sets are the same. So there's 3 random variables. On the left 2 graphs, G1 and G2, we're talking about the factorization. On the right, we're not really saying anything about the factorization. We're saying about the decomposition property. And since it's a clique, it's a 3 clique, it's not really saying anything. So what the left factor graph says is that any probability that can be written in this way as a factor over these 2 variables. So f1 on x1, x2, f2 on x2, x3, and f3 on x3 and x1. So any distribution that can be factored in this way is represented by this graph. On the right, on the middle case, we have an extra factor. So we have f1 on x1, x2, f2 on x2, x3, f3 on x3, x1, and we have another one, which is f4 on all 3 of them together. So it's saying that there can be a factor that doesn't further decompose that involves all 3 variables together. And as an example of like when this might come up, I mean, if you take the log probability, it might be some constant plus some coefficients c ij times the multiplication of the variables. So like if the variables are multiplied up in the exponent, then it doesn't factor. And so you can see that down here, as long as c1, 2, 3 is not 0, that these variables don't, it doesn't factor down in the original probability space. But what about G3? So all G3 says is that there's some factor x1, x2, x3. That's all this really says. Right? It doesn't say, is it pairwise? Is it not pairwise? So G3, in some sense, can cover, in some sense, both G2 and G1, but it doesn't say which one it is. The factor graph has more specificity in that it can restrict the model to only involve pairwise potentials, whereas G2 and G3 doesn't have any sort of restrictive properties. So another way of saying this is that, you know, all 3 of these distributions, P1, P2, and P3, live within G2. It's clear that P1 lives in G1 because that's only pairwise potentials. But it's also clear that P2 and P3 don't live in G1, in G1's family. Why? Because P2 and P3 involve these ternary interactions, the interaction between all 3 variables, and the factor graph on the left doesn't allow that. But on the other hand, going to the Markov random field, all 3 of these distributions, P1, P2, and P3, live in G3. Okay. So what are we to do? So can we stay within the Markov random field formulation with such a limitation. And the limitation basically is the Markov random field's inability to discern the order of the interaction from amongst the variables in the Markov random field's clique. This is true of any Markov random field. You could have a big clique of variables, and you don't know, does that consist of n choose 2 factors, or does that just consist of 1 factor? N choose 2 pairwise factors, or does it consist of 1 factor involving all of the variables in the clique? It's not stated in the Markov random field. So what we can do, however, is just in some sense this is like turning a Markov random field into a factor graph and using the same type of graph without having this bipartite notion. We can transform a Markov random field that does involve higher order potentials into one that has only pairwise potentials, and then we can still use the same belief propagation message strategy that we've been talking about, where we do mu I to j. And we need to use more variables, and the way we do this is the following. Suppose we have this higher order potential, psi of x sub c. And we're saying that it's higher order, which means that its number of variables is greater than 2, strictly. And we're going to create, for that guy, we're going to create a new variable, z sub c. So this is a scalar variable. This is not a vector of variables. Z is a scalar. And z is a scalar in some domain. Okay? And the only constraint is that the size of the domain for z has to be equal to the size of the vector domain for x of c. So x of c could be, x could all be binary variables, but the domain might be 2 to the size of the domain of x of c might be 2 to the size of c. And so that means that now we've got let's say an integer variable or a scalar variable who has 2 to the size of c possible values. So, and it's a monolithic variable in some sense. It's not a vector anymore. And so each sub c sub c represents this value, the vector of values. And just notationally, let's just have a nice quick way of getting back and forth. So x of I of z sub c is a way from going from the monolithic scalar value to the corresponding value of x of I. And then z sub c of x of c is the opposite. It's basically saying, given this vector x of c, how do we go back to the integer value? So in order to do this reduction, let's say we start with a clique. Okay. So the idea is that maybe, let's say that this is x1, this is x2, x3, and x4, and all of this stuff together constitute x sub c. And what we're going to do then is we actually reduce this in the following way. We're going to add pairwise factors between each one of the variables in the original C with this new variable z sub c. So that means we're going to reduce this to, or change this to something that looks like this, where we have x4, x3, and x2, and x1. And we have some other variable over here, which is z sub c. And we add these factors here. These are the factors. Psi sub x I and z sub c. And it's a function of 2 scalar variables. It's a pairwise potential again. It's a pairwise potential along these edges. Okay. And then the last thing we need to do is we need to add one unary potential on z sub c, which gives back the original value. Now, one thing I also want to say is that this, let's just zoom in on this expression here. How do we initiate the values of those? This is the expression there. So basically it's saying that this pairwise potential is such that it gives 0 except for the case when x of I is equal to the corresponding value of x of I associated with z sub c. So it insists that the x of i's and the z sub c's are consistent, so that z sub c acts as a surrogate, and whenever it doesn't, whenever you're considering values of x of c, values of x of I and z sub c that are not consistent with each other, it just kills off those entries. Okay. So they have a very simple value, and then the actual value, the original value of that higher order potential is captured in the value, the new potential, the new unary potential on that new large scalar variable. Now the large scalar variable might be exponentially big, right? It might have a cardinality. The domain size might be exponential, and probably will be. But the point is that we've got now a representation where all higher order potentials have been converted to a new graphical model with more variables, and where everything's pairwise. And we can therefore treat the Markov random field in some sense as having only pairwise potentials. And that is typically what's done, and that's sort of what's implicitly expressed in the Wainwright and Jordan book, that kind of thing can be done. Okay. So any model then has the form of this sort of, any form that has that factor turns into this model. It has like a new variable and this new set of factors. And it uses only pairwise factors. So everything's pairwise again. So therefore we can then, and in some sense you might say, well, isn't this just treating it as a factor graph? And the answer is yes. And then you might say, well, why do we have factor graphs? Or do we want to make these variables, do these factor nodes need to be special? I mean, in some sense, no, they don't, because we can treat belief propagation just as pairwise potentials. And we don't need to, we don't even need to use a bipartite graph where the right-hand side hyperedges have a special square shape or something, or a gradient. They just need to be basically just nodes just like anybody else. And we can just sort of unify the graph, unify the notation, and make things a lot simpler. So that's what we're going to be doing for the rest of this course, basically. There are other options. So one we're going to be doing is this one. So to deal with Markov random fields with higher order potentials, we can actually do this transformation that we just did. Alternatively, we could define belief propagation and factor graphs, like I said, which we're not going to talk about. We could also define belief propagation directly on the max cliques of the Markov random field. Max cliques are in general not hard to get, as you know, because it's an NP-hard problem when the graph is not triangulated to get the max cliques. And what we're going to do, like I said, is this one. Okay, so any questions? Okay. So the other thing that's important, another important concept that we're going to be seeing a lot, is this idea of reparameterization. And so we start with some probability distribution in this family. Okay. And the factors, as we saw this in the junction tree as well. The factors might not have any particular meaning. They might not have any marginal interpretation, or they might not express their behavior in the presence of evidence that's come in, because we might have some unaries far away in the graph that really are unaries with evidence that somehow you need to express in order to have the marginal. You need to have the conditional on those variables, conditioning on whatever that evidence is. And so the idea of reparameterization, that's sort of the name, that's a name that's used to refer to the ideas that of these potential functions sort of adjusting themselves, reparameterizing themselves, so that the overall global probability distribution is the same, but these local potential functions become marginals, or at least have a marginal interpretation. And we saw that in the case of a junction tree. Remember, in the junction tree, we saw that it's possible to do this because of the property of the triangulated graph and the property of decomposable models, that we could actually represent it. If we started with essentially a product in the numerator, a product of clique potentials and divided by a product of separator potentials, even if we start out by defining the separator potentials to be identically equal to 1, that we reparameterize them in such a way by sending these messages such that when we're all done, we have marginals in the clique potentials and also marginals in the separator potentials. So that basic idea is the same. That's what's referred to as reparameterization. We saw this also in the case of a general graph, that it's only possible to do when the graph is triangulated. But we don't want to do triangulation anymore, right? Because we want to do approximate inference. Because triangulated, we know, is going to necessarily potentially blow up the model. If we have a 4-cycle, record it, and we go from R squared to R cubed inference. We want to somehow keep the complexity down, the computational complexity. In the tree, we also saw that we achieved this convergent marginal reparameterization by running the MPP procedure, or running messages that abide by the MPP rule. And we do this until it's the case that all messages along all edges have been sent in both directions, and we saw that once we do that, any further message sends are redundant. The other strategy we also briefly talked about, and the next slide I'm going to make this a little bit more clear, is we could sort of just initialize all messages to be equal to 1, and then just start sending messages in parallel. Every message that could be sent could be sent in parallel until it's the case that we've sent enough messages, namely D messages, where D is the diameter of the tree, and will also have converged. Now, this may not be clear to you, but imagine the following thing. Let's just describe this in the context of an HMM. Or, sorry, just a Markov chain. So here's our Markov chain. So what the message passing protocol says is the following. That you could send this message first, and then you could send this message, and then this message, and this message, and this message, and then send back this way. That would be an abiding message passing protocol, right? Alternatively, you could send that message, and then this message, and then this message, and then this message, and then this message, and then we could start sending messages out. Right? There are lots of valid message passing protocol things you can do in a hidden Markov model. What I'm saying about this parallel thing is that you initialize, and the reason why you can't do is like you can't send this message until you've sent this message, because this guy hasn't, in some sense, isn't even defined. Maybe you haven't even allocated data for that. But what this idea about initializing things to 1 is the following. You just sort of create the data structure associated with every one of these messages and initialize them to 1. Then the first step, you send all messages. The next step, you send messages again. But all these messages, like the green messages, are sent in parallel. And the next step, you send messages yet again. So like all lines of the same color correspond to messages being sent in parallel. And then you do it yet again. What color have we not used yet? And the idea is that you keep sending all these messages in parallel. And at some point or another, I guess if we had one more color, we could do this. Let's use gray. Send one more message. So once we've sent 5 messages, which is the diameter of the tree, we've reached a convergent state because information has propagated from one side to the other side of this tree. So we've done 5 messages, the diameter of the tree, in parallel. Of course, a lot of the messages at the beginning are not really doing anything, but when you think about the first message in one stage, say, and the next message in the other stage, and the next message in the third stage, the next message in the fourth stage, and the next message in the fifth stage, that set of messages, and hopefully you can see that, basically correspond to the original messages that would be sent in series by message passing protocol. And that will, by the same reason we saw before, lead us to a point at which the set of messages has converged, meaning that any further message it sends won't change the state being the collection of messages. So is that idea clear? Now, this idea of a state is really important. So we can actually think of the set of messages in a graph as a large state vector, mu sub t, or mu super t. So to make this also clear, I mean, let's say we have a very simple graphical model. So we have 1, 2, and 3. When you have mu 1 to 2, here's a smaller thing. Mu 1 to 2, mu 2 to 3, mu 3 to 2, and mu 2 to 1. Now each mu 1 to 2 is a function of x2. Mu 2 to 3 is a function of x3. Mu 3 to 2 is a function of x2. And mu 2 to 1 is a function of x1. And if these are binary variables, then each one of those messages is basically an array of length 2. And so you could think of all of these arrays of length 2 sort of concatenated together in one long vector, which in this particular case is going to be of length 8. But in a general graphical model, it's going to be of length equal to 2 times the number of edges times r, where r is the number of possible values in the random variables. Okay, so that can be seen as a big state vector. So we've got this big state vector, mu. And then we could maybe treat sending a message. This is an important concept. So in some sense, today's lectures, the rest of this lecture is like these are these concepts. Sending a message goes from the state at time t, which is mu sub t, to the state at the next time, t plus 1. Right? And in fact, maybe even it's possible to do an update. See a message as mu sub t times some matrix A equals mu sub t plus 1. Maybe treating this as a big state vector, we can see a message as taking the state at time t, hitting it with a big matrix, doing matrix vector multiply, giving us the state at time t plus 1. So this is a state vector representation of message passing or belief propagation. Moreover, what if we did a bunch of messages? If we did a bunch of messages, one after the other, let's say that this message was from, let's say this matrix down, let's move that guy over there. Okay, so this message, A, was really a message from, say, 1 to 2. And we have another matrix which corresponds to, say, 2 to 3. And maybe you have another matrix which corresponds to 3 to 2, and another message which corresponds to 2 to 1. So we have this whole series of matrix multiplies. And when we treat these all together, all these messages that are occurring together could potentially be seen as one matrix A. And so therefore, many, many messages occurring simultaneously can be treated as a big matrix multiply, big matrix vector multiply, to go from state t to state t plus 1. And so what does convergence mean? Convergence means that if we do any subsequent matrix multiply, it would be the case that the state vector doesn't change. So if we could do this, if we could represent this as a matrix multiply, these these belief propagation messages, and we don't know yet if we can really do this, but let's suppose for the moment we can. Some of you probably are going to say, well, of course we can do it. And I'll say, yes, you've anticipated my slide in 2 slides. See, now I've anticipated your question about my slide 2 slides from now. So, and so now you will anticipate me anticipating you anticipating me. Maybe that will happen soon. So don't all laugh at the same time. These are jokes that are, I guess, not funny. One of the things I found about looking back at my own YouTube videos is that, I think I've said this before as well, my jokes are not funny. So you have a right to not laugh at them. But let's get back to this subject. Convergence would mean that if we send any additional messages, the state vector doesn't change from time step t to time step t plus 1. If we could represent these things as matrix vector multiply, and if we had this tree, and if we had sent messages according to belief propagation, we realize that we've reached a convergent state. Any additional messages, which would be any additional matrix multiplies, would not change the state. So what does that sound like to you? It sounds like convergence of the Markov chain, or maybe even more generally, an eigenvalue eigenvector problem. Right? If it's the case that the state is an eigenvector of this matrix A, then all we're doing maybe is just hitting it with an eigenvalue, which is just a scalar, and then we renormalization. I mean, the normalization doesn't matter. Maybe it's just some constant, but we renormalize the potentials. That doesn't really matter. That doesn't change what happens. So the state, we're always, of course, potentially doing normalization. So maybe what we can do is use this idea to talk about convergence in not just a tree, but maybe when we have a loop. Okay, but we want to sort of make this clear. So now, first of all, can we see messages as matrix multiply? So here's a typical pairwise message. All right, and here's the definition of it. So we can, if we loop, or sorry, we group all of these things together. Let's just call them mu sub not j to I. Okay, so just so you know what this notation is, let's put this in one screen. These are all of the messages here grouped together from k to I, where k is not j, and we it's a neighbor of I except for j, and so we're just treating this as not j to I. Okay, and then we have this summation. We're sort of let's go ahead and stick the unary and the pairwise guy together into one function psi prime. But now we can see that this expression, equation 10.16, can be seen as a matrix vector multiply. We have to take the transpose. I mean, if we want to be able to interpret this matrix psi prime as such where it's indexed by ij, where I is the rows and j is the columns, then we have to take the transpose first. But it's just, it doesn't matter. It's just a notational thing. And then we see that this message, since it can be represented as a matrix multiply, it's kind of like a little baby inside of this big matrix A times mu t. We can see that each message is like a little block matrix multiplier. Everything else is essentially zeros except for ones along the diagonal. So you've got a little block associated with, I guess the big matrix would look something like this. It would be mostly ones along the diagonal, except maybe there'd be like a little bit of other stuff here and here. Okay. And moreover, if it's the case that the graph is a tree, we see that by doing this matrix multiply, we will converge after, in the least case, d steps. Meaning, if we do these matrices and we hit this state vector by the appropriate matrix, we will reach a point where no further message and no further matrix multiply will change. And so therefore, we found an eigen vector of, in fact, all of these matrices, because basically any of the matrices corresponding to any of the messages or any composition of the messages are such that the state vector doesn't change other than a proportionality constant. So we've found an eigenvector for all of these matrices, including the multiplication of all these matrices together, which corresponds to multiple messages happening simultaneously. So, okay. Here comes the dangerous part. What happens when the graph has cycles? We start sending this message around a cycle. What might happen? That's bad. We might oscillate. We might never get convergence. Now, let's end the class today, and we will talk about an example of that happening, why it can happen, and ways of avoiding it, and a theorem next time. But I should mention that the theorem that we're going to talk about is the sort of first, I mean, in some sense, in hindsight, it's fairly obvious, but it was really the first result on loopy belief propagation convergence. So, all right, see you on Wednesday.